Annex 69, the name of Annex 69 is a strategy and practice of adaptive thermal comfort in low energy buildings. And the background is how to achieve low energy buildings. The most important three key points is one is appropriate indoor thermal environment. The second is a reasonable architecture design. And the third one is low energy thermal environment control facilities. So now the first one is appropriate indoor thermal environment. We have to use an indoor thermal comfort standard and evaluation index to reflect what is appropriate indoor thermal environment. So it's a key point. But now in the world, for the air conditioning, for the air conditioning buildings, we all use standard to evaluate the indoor thermal environment is PMV and PPD index. And according to PMV and PPD index, that means the narrower control band for the indoor thermal environment, better indoor environment. That means the narrower, the better, but the wider is not so good. Is it reasonable? And in fact, the tight temperature band control will consume more energy. And this literature shows that the narrow control range and the higher energy consumption and the wider control range and the energy saving will be more. So, and the next just now is the air conditioning building. The next one is about free running building without a mechanical system. And for free running building, we are now using the adaptive thermal comfort model. And in fact, the adaptive thermal comfort model is a black box model, and all the data is from two databases. One is R3 RPAA4, we call the R3 database 1, and the second one is SCAPS, as a European database. The all data from the the R3 database data from these countries, and the European data, SCAPS data, is from European countries. But you can see there are no data from Asia, larger Asian country, Africa, and South and Middle America. And although the adaptive effect has been recognized widely by researchers, but the mechanisms have not been yet included in this model because it's a black box model, and it's partially due to the imperfection of the old database. In this black box model, how physiological adaptation, psychological adaptation, and occupant behavior works along with the thermal balance cannot include in this black box model. So what the work first step we have done in Annex 69 is to improve our database. We know that the lack of data from this area, the yellow shadow, so we developed a new database as a database 2. And you can, the database to include the old data and the new data. The green one is a new data. We added more than 180,000 more sets of new data into this database. The data from 6 continents, 20 countries, 60 cities, include almost all the climate zone in the world. And based on the new database, we call the database 2, we developed a 2 adaptive thermal comfort model with some mechanism. One is a SET-based model, It's a SET-based model we call the PTS model, a predicted thermal sensation, and it can reflect some mechanisms. As a linear model, there's a model from a different climate zone in the international climate zones, and another one from different Chinese climate zone. And the slope and the intercept of this line reflect the different thermal adaptation levels. And the second adaptive thermal comfort model is a PMV-based model. And you can see from figures the red one is PMV, typical PMV model, and the adaptive model. The PMV is no matter what condition, and the same temperature as no matter outdoor temperature change, the thermal sensation is the same. So the adaptive model will have the change different from PMV, but this line, black line, shows different kind of behavior adaptation process, include the behavioral adaptation, psychological adaptation, and the physiological adaptation. So that we can, as I say, can explain some mechanisms. And just as we mentioned about the air conditioning model, air conditioning building and free running building. How about the mixed mode building? Because in many Asian countries, most buildings are mixed mode buildings. And what is a mixed mode building? That means free running plus air conditioning. In this kind of building, we have more adaptive opportunities, including the natural ventilation, shading, solar radiation, change clothes, drinking cold drinks, and about facilities include the electric fan, air, and individual control air conditioners, and the next one is a personal control systems. We found that, but now we in this mixed mode building, we used to use air conditioning, PMV, for the air conditioning building as a design criteria. But we found that in the thermal adaptation phenomenon is also present in the mixed mode buildings. So we think use PMV is not good for this kind of mixed mode building. So the second is a reasonable architecture design. We not always high insulation and airtight are reasonable, because high insulation and airtight is just reasonable for the cold climate, but for other climate is not reasonable. And here is I will introduce one case study. One of the case study is a mixed mode office building in Shenzhen, China. It's a subtropic climate. This building strategy, most important, is open. Has open space, natural ventilation, local control, air conditioning. Their energy consumption is just 80% of the local other buildings. This box is annual energy consumption of other local buildings, but the red one, the red cross of energy consumption of this building is just 60%. You can see the open strategy of this building. The people stay outside for group meeting. They feel very comfortable. And even the meeting room, the wall of the meeting room can be fully opened as a door, and the window can be fully opened. And you can also see the corridor, the doorway is open. And in the air conditioning period, the indoor parameter is the blue dot, and the red dot is natural ventilation period. But you can see even in this building, during the air conditioning period, the indoor parameter, more than 90% of indoor parameter as outside of archery comfort zone, but more than 80% people feel comfortable as acceptable. And the second case is office building in Guian, China. It's a free running building, zero energy building, because it's located in moderate climates. And their strategy is a ceiling fan and underground duct ventilation, natural ventilation, daylighting, and and so on. The third one is an office building in Wollongong, Australia. It's in maritime climate zone. It's a mixed mode building. And you can see there have the adaptive opportunities, the window control, PC personal comfort system, and the natural ventilation. We open for natural ventilation. And the fourth one is the office building as in India. It's a mixed mode building in Ahmedabad. It's a hot climate zone. Adaptive opportunity for this building is a personal fan, window opening, and closing change. And the electric consumption is 57 kilowatt-hour electricity per square meter a year, even lower than Shenzhen's building with equipment load. Without equipment load is a 38 around as for air conditioning. Okay, finally, we can see the low energy environment control facilities. Now I would like to talk more about traditional HVAC system. I will focus on PCS as personal comfort system. What is a personal comfort system? It's a virtual device that provides personal environment control of the included the thermal and air quality. Here, there's a picture. You can see the ambient environment can be quite loose, but everyone can make their own microclimate. This one is a concept of heating, local heating, and this one is personal cooling. And this picture shows different kinds of personal comfort system. PCS terminals. You can see different ceiling fan, desk fan, standard fan, and feed heater, and ventilate, and also ventilation system. And this one is some real things. There's a heating and cooling chair. This part is a heating cooling chair developed by UC Berkeley as it can be used for heating in the winter and cooling. Use fan for cooling in summer, and the total maximum power is of 14 watts for heating and 3.6 watts for cooling. And this one is a cooling chair, and a conducted cooling chair developed by Tsinghua University. The experiment is made by semiconductor refrigeration system. And this is a different kind of PCS developed by UC Berkeley. Desk fan, warmer, heated in slow, and various pad. Various pad can be used for both heating and cooling for the hand. And the scenario for using PCS in UC Berkeley. You can see that here. And the Tsinghua University developed a conducted cooling chair. The cooling chair, we finally, I wouldn't like to explain in more detail, but the conclusion is that the conducted cooling chair, the surface temperature demand is just from 25 degrees to 28 degrees. The subject can keep thermal neutral even when the ambient temperature is 30 degrees. They feel neutral. And the ambient temperature is 32, they feel slight warm but acceptable. So this is totally different from traditional air conditioning, because the demand temperature is quite high. And the local cooling can significantly reduce the overall thermal sensation and improve the overall thermal comfort. This compare the control growth back cooling and backstop cooling and the post cooling, combined cooling. You see they can feel neutral. The corrective power can be 2 to 4 degrees. That means when you feel 28 degrees or 30 degrees, you feel just neutral 28 degrees. So we have a very more potential energy saving. Here is a variable PCS like cooling garment.
Versus you.
And
a couple of minutes, just 2 minutes, please, if you would.
Okay, almost finished. The final two slides. Two slides. One is we do the estimation for the energy saving potential, and for if indoor temperature from 26 to 30 to change it to 30 degrees. So we most of the case we can use natural ventilation, and the energy air conditioning energy consumption, cooling energy will reduce by 70%. What it means 70%? The electricity consumption for cooling in Beijing office building is about 40 kilowatt hours per meter per year, and 77% energy saving means is the energy consumption is just 9.2 kilowatt hour per square meter per year. But the electric consumption of the fan of cooling chair UC Berkeley in UC Berkeley is just 3.6 watt per chair. That means in 1 year, one chair occupied 5 square meter means 0.6 kilowatt hour electricity for 1 year per square meter. But for contact cooling chair, of course, the semiconductor refrigeration is not efficient, but electrocaloric effect is a very promising micro refrigeration approach because the COP can high to 10 degrees. The temperature range is just good for us. We need is around 27 degrees, and the ambient temperature is 33 degrees. And you can see this material is soft, can be used to contact a garment or chair. So there's a very promising facilities. Okay, now the Annex 69 will develop the deliverable. One is a guideline for the low energy building design. Another one is for PCS development. And of course, the third deliverable as a database too. Thank you for your attention.